Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside, and we are beginning a venture in our Integrated Math 2 Big Ideas Math series, where we start Chapter 1, Section 1. Chapter 1 is on functions and exponents. Section 1 is on absolute value functions themselves. We're going to take a look within this book of Big Ideas Math. If you'd like to follow along, I'm going to attach a PDF link in the description section down below, hopefully with timestamps to follow on the problem set that we do. But we can go ahead and take a look at what is, give me 1 second here, and there's going to be a large problem set afterward, where if I run through this stuff faster in the beginning, my plan is to go through the problem set pretty fast, because the problem set has a lot of problems. I mean, like 60. So we're just going to kind of go through those a lot faster, especially once we hit a problem that we've seen or a concept that we've seen before. So some phrases or some target terms you're going to hear, we're going to be translating graphs, we're going to stretch and shrink, I might say compress, and reflect graphs, reflecting across the x-axis, these absolute value functions, these v-shapes here. An absolute value function, we use this symbol, that absolute value, the bars. To you, that might mean make things positive, and for a number, that's kind of the case. A number inside, like -3, does become +3. It's this absolute value because it is its distance from 0. -3 is 3 from 0, 3 is 3 from 0, and that's what works out here. The parent function, the absolute value of x, looks like this. Whenever x is 1, y is 1, x is 2, y is 2, or -1, y is still 1, because that is the output for that input, like that. And then it angles at what's called a vertex. This vertex is going to be a target word, a huge word we're going to be using. Let's see if it's one of those things on here that'll actually say it up above. And then it is linear in nature on both sides, and it continues forever in its infinite domain of all real numbers as long as we're not restricting it. The range is limited by the vertex. The graphs can go upside down. We're going to take a look at some of those when they reflect. There are different kinds of transformations that they can have. You're going to see different forms of this. If there's a plus something on the outside, that is a vertical translation of some sort, like this one, this +3 going 3 up for the vertex, and the entire graph goes up with that. If it's something on the inside, this x minus h, we're going to talk about that a little bit more, but it's a horizontal translation, like this thing right here. Again, I'm not running through all the notes. I'm just kind of giving you the ideas of what's going to happen. The value inside is opposite for a specific reason. It has to do with the x value we're choosing. For x minus 2, we'd have to choose an x value of 2 to make the inside 0. So there's an opposite effect, whereas this thing we're trying to affect the y value. The y becomes 3 greater than what it originally was. That's why it's flipped on the inside, but not flipped on the outside. There's a lot more to it we could talk about. I'm trying to think about how to do this a lot faster and talking about it. Stretching and shrinking and reflecting all has to do with some a. This a value is a value that's multiplying by the absolute value function itself. So, I mean, it's a number. So, as long as it's non-zero. If it's 1, then it's implied, and you won't see it out there. It's just like x is 1x in that way. And same with the -1, you just see a negative and then absolute value of. But if it's 2 or -1/2 or something like that, then it affects it. Think like a slope has a rise over run kind of concept, and we're actually going to be utilizing that here. When you have 2 in front, this graph vertically stretches. It becomes twice as tall for the same x value. For the original parent function in black, now the new one is twice as tall. So you see, instead of going up 1/1, we're going up 2/1 from the vertex, like so. And then when you have a -1/2, the 1/2 portion is a vertical compression. Things become half the height over 1 down 1/2 over 1 down 1/2, or over 1 down 2. Excuse me, down 1 over down 1/2 over 1. Down 1 over 2, and the reason we're going down is because the negative portion of this thing, that negative is making it so. I'm going to ignore using tables when I do the graphing itself, so I hope that it's kind of making sense with that. So we've already seen a few things here. We've seen horizontal translations, vertical translations. We've seen vertical stretches, compressions, and reflections based on the letters A, H, and K. So when you put it all together, there is this form right here. Some function, some y equals, g of x is like y. A times the absolute value of x minus h plus k. A can't be 0. The vertex of your graph will be at h comma k. They're showing that right here. This is known as vertex form of your graph. This is going to be a very popular thing you're going to see through not just absolute value functions, but a lot of other functions where there is some sort of center, in our case the vertex, and then it behaves like an absolute value from there in the V-shape form. So that's mostly what I want to point to here right now. That's just my lead into what we're going to be doing for our problem set, whether it's the graphs or writing equations or talking about transformations, all that kind of stuff. So just be prepared for a bunch of that. Before we actually get started on the official problem set, there are these first 4 problems where we do vocab and core concept check in what's going on. I want to lead you into what that forms actually look like. Then we'll start hitting that number 5 through something. Okay, complete the sentence. The point 1, negative 4 is the blank of the graph of f of x equals negative 3 times x minus 1 minus 4. This is going to be the vertex of the graph. The 1 is the h, the negative 4 is the k. Remember, the form says x minus h, so x minus 1, and then plus k is plus negative 4. It represents the vertex. Number 2, how do you know whether the graph of boom is a vertical stretch or vertical shrink on the graph of this? So what they're saying is compare to the parent function, how do you know whether this is a stretch or shrink? Now, the stretch or shrink has nothing to do with h and k. It has to do with a. If a is greater than 1, you're looking at a stretch. If a is between 0 and 1, you're looking at a shrink. Now, that is if the graph goes upward. If it's less than negative 1, if it's like negative 10, then it's going to stretch downward, and it's still called a stretch even though it goes downward. So what we want to do is mention if the absolute value of a is, because if a was 10 or negative 10, its absolute value does become 10 regardless, and we want that to be greater than 1. So this is the stretch, and this is the shrink. Number 3, I'm sorry, whoopsie. Let me lock that in. Stuff I hadn't prepped for. And number 3, describe 3 different types of transformations of the graph of an absolute value function. There's translation. There's stretch or compression. I prefer to say compress instead of shrink. Hopefully you know what I mean. So it compresses. And then it's fine either way what you say. And then there's a reflection. If the graph becomes negative, if the a is negative, then the graph goes upside down. So those are the 3 transformations. The graph of which function has the same y-intercept as the graph of f of x equals absolute value of x minus 2 plus 5? Explain. Now, you want to be careful here. We're not looking for vertex. We're looking for y-intercept. That's the value of y when x equals 0. So the question is, what's the y-intercept here? Let's substitute 0 into there. 0 minus 2, plus 5. Absolute value of negative 2 is 2. And 2 plus 5 is 7. So the y-intercept of this one is 7. And the question is, which one here would give us 7 if we plugged in 0? Let's do that kind of manually. 3 times 0 is 0. Minus 2 is negative 2. Absolute value of that is positive 2. Plus 5 is 7. Looks like that one matches. That looks correct. This one, when you plug in 0, absolute value of negative 2 becomes 2. Times 3 is 6. Plus 5 is 11. So it looks like it's going to be that one. It shares the same y-intercept. When I substitute in 0, that's what I get. That's without graphing it. Okay, so those are some concept checks. We're going to start on the number 5 stuff onward from here. And again, hopefully if I plug in some timestamps, I'll at least do them within the sections or something like that. And you can follow along with me as such with the PDF and binder paper or what have you along the rest of the way. So without further ado, let's go ahead and get started on this big problem set. And what you'll see on the screen with me, sorry, give me a sec. Let me, this is my first time kind of doing it this way. What you'll see on the screen with me here is numbers 5 through 63, if you look down below right there. 5 through 63 is the rest of the way in this 1.1. Okay, so this number 5, as we start off, graph the function, compare the graph to the graph of f of x equals absolute value of x, the original parent function, describe the domain and range. Now, we'll do that. Okay, so for number 5 here, okay, we got to graph them. So I'm going to pull out this guy. Guess I got to do this for all of them. So absolute value of x minus 4. D of x equals absolute value of x minus 4. So in vertex form, the a is 1, the h is 0, and the k is negative 4. The K is the vertical translation. That represents our vertex. We will shift 4 down. We do not shift left or right at all for the vertex. The A is 1. That means just like the original parent function, we will just have a rise and run of 1 for the graph, both to the left and right of the vertex for this particular graph. And as we go to the left side, remember it also goes up. All the graphs have the V shape with respect to the vertex. The reason for that being when you take the absolute value of a negative number, it still becomes positive. Let me try to get my colors. And we will draw those lines. You must draw arrows on those lines because now we're going to talk about the domain and range of this thing. This guy's domain is all real numbers. It goes forever left and right. Don't expect anything different on these unless they do something to restrict it, which I don't see anything that they're going to do. This range here, the y values are as low as -4, and they go above it. Greater than or equal to -4. Those are, so like that, though. Okay. All right, let's move on to number, give me 1 second here. Let me figure this out. I'll just scroll down. Let's move on to number 6. This isn't going to be as easy as I thought when it comes to navigating this. There we go. Number 6, I'll just leave the thing on the screen there. Absolute value of x plus 5. The A is 1, the H is 0, the K is 5. So this time we'll shift 5 units upward like so. And with the A being a positive 1, like so, both directions. Now, I'm simulating what I would expect my own students to see when it comes to plot every point you can fit on the graph. At some point, I'm probably just going to rough through it and say as long as I got the slope right, then we're good. And you'll probably see that in the future. The domain, once again, is all real numbers. The range is y is greater than or equal to +5. They go upward from there. Okay. All right, number 7. Absolute value of x plus 1. Now this time the plus 1 sits inside of the absolute value function. So this represents the h value in a way. Remember, it's x minus h. How does it become a plus 1? The h has to be negative. X minus -1 becomes x plus 1. You plug in -1 for x, then you get 0 inside the absolute value. That's kind of what reveals your vertex, if you will. The h is -1, k is 0, a is 1. This time we shift 1 unit to the left. 1 unit to the left for the vertex. The a is still 1, and if you don't mind, I'm just going to go up 1 over 1. Boom, just like that. Again, it's one of those things where after we've done a problem like it, I'd like to probably go forward a little bit faster. You can pause as you need to. The domain, once again, all real numbers, unchanged. The range is y is greater than or equal to 0. This vertex has no effect on the y value. Whoops, you can't see that. This vertex has no effect on the y values itself, right? This is just, it just is as it is. So we respect that. We make it so, like it is. All right, number 8. Absolute value of x minus 3. And I have to pause after this for 1 moment. I want to fix something on my next slides. Let's do this right here. Let's get rid of that. Absolute value of x minus 3. This time the h is positive 3, so we are going to shift this guy 3 units to the right. So 1, 2, 3, like so. The a is 1, the h is 0. Excuse me, the k is 0. And so no vertical translation, no vertical stretch, compression, reflection. So the graph's going to go like that. Domain, all real numbers. Range, y is greater than or equal to 0. Give me a second to fix something on here. Okay, hopefully I fixed my need there. Let's move on to number 9. 1/3. P of x equals 1/3 times the absolute value of x. So this guy is vertically compressed. The a value is 1/3. The h and k are 0, so our vertex is at the origin, just like so. Now, I'm not going to go up 1/3 over 1. If you remember things with slopes, if I go over 3 times, then I should go up 3 times the amount of 1/3, which is 1. Up 1 over 3. So up 1, right 3, and then everything that's hit before that, like in between, applies. That means up 1/3 over 1 is hit. I just don't need to actually hit that as a fraction. And up 1 and 3 to the left as well. So we're going to see that. So I'm not intimidated by slopes that have fractions by them. In fact, sometimes I prefer them. I prefer more than 2 because I need to make sure that I go over 1. I mean, I'll know to do it, but it's just, it's one of those things to just be sure of. All right, number 10. I have to paste these in each time. That's the only problem. J of x equals 3 times the absolute value of x. This time the a value is 3. The h and k are 0, so we're going to start here again. Up 3 over 1. And if you want to try this instead, you reflect across kind of that axis of symmetry. Up 3 over 1 like that. Maybe that's a faster way for you to do it instead of continuing on the same path. Or maybe not. It's giving you options. But you can see this one's a vertical stretch compared to the other one that was a vertical compression. So that's number 10. Number 11, a of x equals negative 5 times the absolute value of x. So on this one, the a is negative 5. And a negative 5 means, negative means the reflection across over the x-axis. So h and k are 0. We are going to start on the origin, and we will go down 5 each time. Remember, taking the absolute value of something turns it positive. You multiply by a negative, it's going to turn it negative. So no matter what, these numbers become negative. Down 5 over 1 each time. I'm going to plot what I can fit just like that. Down 5 over 1. Okay, I'm just making sure I can see on the screen. I got a lot of screens open. This is going to be a hassle. I only have one screen. Although it's ultra wide, I need multiple screens for this to be as efficient as possible. I couldn't fit it on my workstation though if I wanted to. Number 12, once again, not intimidated by the fraction in the least bit. Oh, I haven't been doing domain and range. I apologize. Let me state them out loud for the sake of what we've been doing. Domains are all real numbers, okay? Range, y is greater than or equal to 0. Y is greater than or equal to 0. Y is less than or equal to 0. What's this one? Y is less than or equal to 0. We start at the vertex. Basically, the vertex represents your maximum or your minimum of your graph. That's the absolute highest or lowest point it can go. Lowest if it's this way, highest if it's that way. This one will go that way because it's a negative 3/2, down 3, right 2, plot a point, move on, and the highest y value that we hit is 0. It doesn't matter if we translate to the left or right any. It matters if we translate up or down any, and we didn't for either. So in this case, less than or equal to 0. Domain's all real numbers because as you can see, although this graph goes down forever, it also goes left and right forever. So that's why domain of all real numbers applies, and range y is less than or equal to 0. Now we include 0. It's one of the points on the graph. Okay, let's move forward to number 13, or this section. In exercises 13 to 16, graph the function. Compare the graph to the graph of f of x equals absolute value of x minus 6. So what I'll do this time is I'm going to graph that first f of x graph. I'm even going to write it down here, and I'm going to color code it differently. I'll call this f of x. So this graph is going to look like so. 6, not negative 6. 6 is your h value. Slope of, if you don't mind, I'm just going to go ahead and, actually, I'll keep it. I'll draw this one. Maybe the other ones I don't. Slope of up 1 over 1. Just kind of put little points though. Okay. And I'll leave this one on the screen. What official green am I using? Is it this one? That's a little darker. That's okay. Okay, so that's our parent function. And keep in mind, this thing goes left and right forever. It's not more left and up than this way. That's just a window range thing. And then what I'm going to do is I'll probably just stay on this page for these 4, and then I'll graph them all separately. So number 13, I'll just keep in blue. We are going to have h of x, which is x, absolute value of x minus 6 plus 2. So this one also goes to the right 6, but now that plus 2 is our k value, that actually does translate this thing 2 units upward. So this graph will look exactly like this other one, except it's going to be 2 units upward. And that's the end idea of what all the translation of all the transformation stuff means. It looks just like this one with the stretch, reflection, or lack thereof. And the translations, except this translates up to more than the other. Number 14, n of x, look at n of x, it's 1/2 absolute value of x minus 6. And by the way, I'm verbally describing the transformations here. It translates 2 units upward in comparison to the absolute value of x minus 6. This one also translates the same way as the green does, the original parent function. The vertex is at 6, 0. Only now there's a vertical compression by a factor of 1/2. That's how you say that. Vertically compress by a factor of 1/2. Everything is 1/2 times the size in the y direction compared to what the green was. And that's tough to see for people sometimes with an infinite domain. I'll show you what I mean when I graph this one here. Okay. So I go this way, right? If I go out here, you might say, oh, this graph goes more left than the green and blue ones do. No, they all go left forever. See, I didn't stop it the same amount that I stopped this one. But when you compare the two like that, if you ignore those dots and you just compare green to purple, you can just see that everything is half the height that these ones are. The fact that I draw it farther out just because I can fit it in the window range is, irrelevant to the fact that they both go left and right forever. But this is vertically compressed by a factor of 1/2. I'm sorry, I was not changing the circles on here. That was number 14. Number 15. Number 15, let's see, color red. 15k of x, -3 times absolute value of x minus 6. It once again has a vertex here. And -3 is a reflection over the x-axis. And we vertically stretch by a factor of 3. In comparison, again, we are comparing to the original function, which was absolute value of x minus 6. There's no change in translation to that function, to the green function. Right? There's no change in comparison to that, but there is in a reflection over the x-axis and then a vertical stretch by a factor of 3. We wouldn't say -3. The negative was the reflection. And last one, I might as well just use black. I'm actually limited in colors that I have. There we go. G of x equals absolute value of x minus 1. This changes the vertex this time. Absolute value of x minus 1 is over here. But that seems to be the only thing that changes. Not slope, but the stretch factor. I mean, I go up 1/1. So there's no change in stretch factor to green. Maybe it is faster to draw dots sometimes. There is no change in stretch factor compared to green. If you look at black versus green, what's different? This is only, this vertex is at 1, 0. This vertex is at 6, 0. We have to compare it to green. So what's our comparison? We translate the green graph 5 units to the left, and then it becomes the black graph. I know it's translated 1 unit from the origin, but they're asking us to compare it not to the parent function absolute value of x, but absolute value of x minus 6. And that's exactly what we'll do there. Okay, moving forward, let's take a look at numbers 17 and 18. Graph the function, compare the graph to this. So it's going to be the same concept as what we just did, only now more. So the original f of x equals absolute value of x plus 3 minus 2. We have -3, -2 as this guy's vertex. That is our h of -3. Hopefully you're getting used to that. Change the sign. It has to do with what we do plugging for x. K, we keep the sign. And then we plot it there. The a value is 1, so I'm going to give that one a faster skidoo. The only problem is I have to look at where it's actually, I have to make sure I'm actually going up 1/1, and that locks differently. Okay, so here is the parent function. Or here's the original. Here's the function we're comparing to, I should say, for numbers 17 and 18. Okay, here we go. Number 17. Let's just do it in blue. I don't think I need to call it y of x for you. You just know it's in blue. Hopefully, no color blindness. Number 17. Y of x equals absolute value of x plus 4 minus 2. So x plus 4, we're going to go 4 to the left, 1, 2, 3, 4, and then minus 2 is down here. Same graph otherwise. A is the same. Even the k is the same. So what's different from green to blue is the question. How do you describe that? Translate, and that word's important, right? We try and use those transformation words. I'm going to use compression instead of shrinking, but translate f of x 1 unit to the left. Number 18 is b of x. 18 b of x, absolute value of x plus 3, so 3 to the left, plus 3 up. No change in a. So it looks like so. Okay, compared to green, translate how many units up from green? 1, 2, 3, 4, 5. From -2 to 3, translate 5 units up. And those are the differences. That's what we're doing. Okay, let's move on to numbers 19 and 20. Number 19, compare the graphs, find the value of h, k, or a. Now the black graph is just that parent function absolute value of x. We can mostly just ignore that. We're looking at the g of x's in this case here. So number 19, g of x equals absolute value of x plus k. Now, if you compare the graphs, this g of x is translated 3 units down from the original f of x. That's the difference. So we translate 3 units down. I might type this later if they ask us to do this in the future. That means k is -3. So when they see absolute value of x plus k, I mean h is 0, a is 1. That's, we just kind of leave them. We don't write anything. This is going to be g of x equals absolute value of x minus 3. And that would be number 19. Number 20, t of x equals absolute value of x minus h. And that's inside. Again, the parent function is just absolute value of x. So number 20, we translate 1 unit to the right. If you notice the blue is 1 to the right. So translate 1 unit right. That gives you an h value of 1. Positive 1. Now, the equation has a minus in it. It's, you see it, absolute value of x minus h. That's actually how the parent function is designed to look. So this will say x minus 1 inside of the actual function itself. And that makes it behave like we want it to. That's what's going to allow it to do exactly that. Okay, we're going to move forward now to number 21 and 22. These are more of the same, so I'm just going to go ahead and continue onward. So number 21, in the same vein, let me type these actually now, if that's okay. Let's see if this works. Well, okay, so what happens? Blue this is now about A. There's no translation things, right? The translation, no left, right. So nothing there. It's about stretches and reflections. I'll start with the reflection. It goes upside down. Reflect over x-axis. That way, you already know that we don't have to, mention anything about the negative anymore. It's taken care of. And by the way, technically, you are supposed to mention reflections and stretches and compressions before translations, because reflecting over the x-axis happens. If I translate upward and reflect over the x-axis, it would go upside down, like that. But I want to reflect it first and then go up. So you should always mention those first. So reflect over x-axis, and then vertically stretch by how much? Originally, we go up 1 to go over 1 each time. Now we're going down, which we already accounted for that. 1, 2, 3. We go down 3 as we go 1 over. So vertically stretch by a factor of 3. So those there. That makes the a value -3, which means the equation will be, what is this? P of x. P of x equals, I should write that. That was just for translation stuff. I think I'll write them. I'm playing with this a little too much. P of x equals -3 times the absolute value of x. Number 22, I don't seem to be going faster than I normally would in any other case, but hopefully you're learning it. No reflection over the x-axis. It's an upward facing graph, so nothing changed there. but there's a vertical compression this time. Up 1 over 2, so up half, over 2 to go up 1 instead of up 2. So, 1 half. The A value is 1 half. We vertically compress by a factor of 1 half. Now, there is an argument to be made, and I don't know which way the book does it. I assume they do it just like this. There is an argument to be made that you might know in division, if I divide by 1 half, that's not the same thing as dividing by 2. Dividing by 1 half actually means multiplying by 2. So there's an argument to be made that when I say compress and then I say 1 half, that's kind of like the dividing by 1 half kind of thing. You know what I mean? That I'm not, give me 1 second, that I'm not, I don't know. The fact that we're saying compression is just a courtesy for things. The 1 half factor is the A value. That's how I want to say it, basically. All right, anyway, this is like that. There's no change in, once again, the vertex on that. Okay. See, it's the graphing that slows me down normally. All right, 23 to 26. Write an equation that represents the given transformation of the graph of g of x equals absolute value of x. For all of these, I'm just going to call them f of x equals because they use g of x for the parent function, the original. Vertical translation 7 units down. That is a k value. K is vertical translation. 7 units down means minus 7 outside the absolute value. If you recall, it's the, I'm going to say, let me do this first. F of x equals a times the absolute value of x minus h plus k. That's our k value. Now, nothing else changed, right? You took g of x, absolute value of x, and we translated 7 units down. So there's no change in a, there's no change in h, only k. That's the idea. Number 24, horizontal translation 10 units to the left. That makes h become negative 10. The h value is negative 10. X minus negative 10 is x plus 10. So inside the absolute value function, x plus 10. That's what causes that translation. Excuse me. 25, vertical shrink or compression by a factor of 1/4. And that's where I just went back to my philosophical conversation about what would they say. If they said vertically shrink by a factor of 4, I mean, that makes sense to me. Make it 4 times smaller. But the 1/4 is literally what we're referring to when it comes to A. So A is 1/4. And that multiplies by the absolute value of x. That affects your y becomes 4 times smaller as a result of that. And last one, 26, vertical stretch by a factor of 3 and a reflection in the x-axis. I say reflect over the x-axis. It's the same concept. The A is negative. Excuse me. The A is negative, so we're going to say f of x equals negative. Sorry, I was looking at a text. And the factor is 3. Vertical stretch by a factor of 3. X. And that's it. Okay, numbers 27 to 32. Graph and compare the two functions. Okay, it's a lot of graphing. Now, before I begin, and by the way, I'm going to verbally compare them. I'm not going to write it out. F of x is this blue. Now, g of x I'll make green. I got to do some things to g of x, and I'll talk about it after I graph f of x. Because this is not in vertex form, and I'll show you, I'll kind of demonstrate why. But we'll get to that. All right, f of x equals absolute value of x minus 4. 4 to the right. And up 1 over 1, both directions. There. And yeah, it's about that. G of x, okay, is the vertical stretch 3 or 1? Already a good question within. Is h negative 4, excuse me, is h4 and k is 0. Let's answer the h thing first. H is not 4. The vertex requires that you plug in a value for x that makes the absolute value 0. That's what minimizes or maximizes your value when that becomes 0 inside. If I plug 4 into there, I don't get 0 out. What value would I need to plug in to x to get 0? If you get it in vertex form, it answers that question. You can also set this equal to 0 and solve. I'll tell you right now that value is 4/3. Now here's what we're going to do. The reason it's not in vertex form is because there's something multiplying by x inside of the function that shouldn't be there. So that 3 needs to factor out, like so. 3 times x minus 4/3. Now what I just did in factoring was I divided 3 out of this portion. 3 got divided out of it. Everything became 3 times smaller. 4 is 3 times smaller. 3x is 3 times smaller. There is a property you can use with absolute values that a product, this is 3 times this quantity, I can separate that into 2 separate absolute values like so. Absolute value 3 times absolute value of x minus 4/3. And the absolute value of 3 is 3. So this can be rewritten as 3 times the absolute value of x minus 4/3 like so. This is your g of x function. This gives you an a value of 3, which that answers that question, but the h wasn't 4, it's 4/3. 4/3 is also 1 1/3. Not my favorite when we have fractions for these because I have to use it the whole way, so 1 1/3 kind of like that. And I have to go up 3 over 1 from here. It gets weird. Up 3 over 1, now I'm at 2 1/3. Up 3 over 1, now I'm at 3 1/3. That looks more like a quarter, but that's okay. But hopefully that makes sense kind of what I'm doing and how this came to be. Now this is at 1/3 and negative 2/3, I guess, and negative 1 2/3. So those are the two graphs. Okay, this is just for one problem. All right, I graphed them. Compare the two. Translate. I don't know. From F to G. From F to G, G is a translation 2 2/3 units to the left, because we're at 1 1/3 there. So 2 2/3 units to the left, that's 1, 2, 2/3. And then vertically stretched by a factor of 3. So that's my description on that. Okay. Number 28. They want us to have a lot of fun with these. Let's go. So all of these seem to have that factor business, basically. I hope that makes sense. Okay, f of x, or excuse me, h of x. H of x equals absolute value of x plus 5. In which case, I'm going to go faster on these now. I hope that's okay. H is negative 5. Not h as in h of x, but as in x minus h. A value is 1. T of x equals, can I do this in one step? Factor the 2 out. That'll be from the absolute value portion. And then x plus 5 halves. Everything inside becomes twice as small. That's what it should look like compared to what you're seeing on the left side. So let's graph that. Negative 5 halves to the left is 2 1/2 to the left. And then a vertical stretch of 2. Up 2 over 1. You know what I could do is I could go up 1 over 1/2 like that, and then I could stay on this path up 2 over 1. This is still up 2 over 1. I just found a better place to do it on, like right here, and then just go forward. There we go. And if that doesn't make sense, then you can continue on the way that you were doing it. It should still be the same graph regardless. See, it still goes on the line. There's no change. Okay, compare h to t. To go from h to t, we got to translate 2 1/2 units to the right, 1 2 1/2 units to the right, vertically stretched by a factor of 2. I should say the stretch first. Vertically stretched by a factor of 2, translate 2 1/2 units to the right. Okay, number 29. P of x equals absolute value of x plus 1. That's translated 1 unit to the left, and then once again stretch of 1. Or no change in stretch, if you will. This one seems to have the change, however. Now this one, I need to... Oh, -2. I didn't see that. There's a -2. Okay. Good thing I have a tool where I can just translate it. Like that. Okay. Q of x... I need to write a little bit more with this one. 1/4 absolute value of 1. And the only reason I noticed the -2 is because this one had a -2. X plus 1 minus 2. All right, I'm going to do the same things I did last time. This 1/4 will factor out. But it only factors out of these two guys here. Now, what happens when you factor a 1/4 out of something? The stuff inside doesn't become 4 times smaller. It becomes 4 times larger. So instead of x plus 1/4, this should become x plus 4, like that, -2. Actually, didn't really need to write anything more than that. But this is what we're going to be using like that, so plus 4. Plus 4 does mean 4 units to the left. And then down 2 for k. And the 1/4 is our vertical compression. Up 1/4, like so. Okay, let's compare these two. So let's first state the compressions, the compression. We are vertically compressing by a factor of 1/4 from blue to green. It compressed. And then we translate 1, 2, 3 units to the left. Okay, number 30. I won't write. I don't think I need to write the function. Yeah, I do. Okay, let's see. Because I need you to know what colors I'm using. W of x is absolute value of x minus 3 plus 4. All right. 3 to the right, and whoops, and 4 up is the vertex. Stretch of 1. And hopefully you're hitting those same points. Y of x, let's just write the factored form. Hopefully it's making a little bit of sense. I factor a 5 out. Inside is x minus 3/5. 5 times smaller, just for the inside quantity. This plus 4 is still plus 4. That shouldn't change. I just don't like doing these fraction things. I mean, you probably don't either. 3/5, it's a little more than halfway, but 3/5 to the right, just like that. Up 4, just like that. It would have been nicer if they just made sure these weren't fractions, at least not so many times. And up 5 over 1. You know, we're changing books, at least with these videos. You get a book change, and I like the idea of challenges here and there. That's completely okay to have challenge within. But for this being the first time you saw the factoring portion, I'd like for it to have introduced the concept first with cleaner numbers, and then you go from there. So can't poo-poo on the book just yet. I should be endorsing it. Okay, so from here, there is a vertical stretch by a factor of 5, and translate 1, 2, and 2/5 to the left. Remember, it was 3/5 to the right of here, so 2/5 to the left. Translate 2 and 2/5 units to the left. Number 31. A of x equals absolute value of x plus 2 plus 3. 2 left, 3 up, stretch of 1. Oops. B of x. Okay, I'm going to write this one out. Let's start with the factor portion. I'm going to factor a -4 out. I'm not doing it out of the absolute value yet. Let's do one at a time again. Let's factor -4 out of the quantity. Here's x. What's 2 divided by negative 4? That's the question that you're asking yourself when it comes to this factoring portion. That answer is negative 2/4 or negative 1/2. And let's leave it in fraction form. No decimals. Negative 1/2 like so. It's negative. It's not positive. So that's one big thing about this that you have to make sure you're aware of. That plus 3 is unchanged. Now, the next part is also a little tricky. Remember how I showed this other step in between, that there's absolute value of these two things that are split apart like so, before we kind of get that last part. The absolute value of negative 4 is positive 4. So that's a positive 4 here, and you got absolute value of x minus 1/2 plus 3. Now, you may be asking a couple questions here. For one, and the question that I really haven't gotten to before was, why didn't this turn into x plus 1/2? Well, we don't know what x is. I mean, we're not solving for it. X is in infinite domain. X can be anything. But that x minus 1/2 is a single quantity. You don't turn minuses into positives. Negative values have a positive absolute value. We don't know what's negative and positive here. This is an entire graph and spectrum, so there's nothing to turn into there. But also, well, then what's the difference of having a 4 or a negative 4 inside there if it's just going to turn positive? It changed h. H went from what was seemingly a plus 2 to a minus something. So it did change something still being negative. So we're going to go, instead of 1/2 to the left, we're going to go 1/2 to the right. That's what the minus 1/2 means. So 1/2 to the right, then plus 3. And the stretch of 4. 1, 2, 3, 4 over 1. Like that. So there's the graph. Okay. Vertically stretch by a factor of 4 and translate 1, 2.5 units to the right. All right, last one in this section, number 32. I don't think we're halfway done with the problem sets, so hopefully they don't go as long later. Or maybe they do. They tend to get harder later, don't they? U of x equals... If you got my update thing, channel update, I planned on doing a lot of these over the summer. It didn't pan out, and you can see why I really wanted to do it then. V of x, okay, let's see if we can do this in our head here. You factor out the negative 1/2, and inside the absolute value will become x plus 2. If you have trouble doing that, think about negative 1/2 times what gives you negative 1. In this case 2. You factor the negative 1/2 out, take its absolute value, becomes 1/2, positive 1/2. And then plus 2. That's the newly written version. You want vertex form. As far as graphing goes, unless you're using a table, you want vertex form. So the blue is 1, 2 for a vertex. Up 1 over 1. The green is left 2, up 2, and a vertical compression of 1/2. No reflections. We go up 1 over 2, kind of like that. I say kind of, because I don't know what's up 1 over 2. I'll just kind of do this. Boom, boom. I should do that in the future anyway. Okay. From blue to green. Vertical compression by a factor of 1/2, and translate 1, 2, 3 units to the left. And there you have that set, unless there are more on this other side. Doesn't look like it. All right, number 33. Describe the transformations from the graph of f of x equals absolute value of x to the graph of the given function, then graph the given function, of course. I guess let's try and describe it first. I am going to type these out this time. Number 33, so the original is just the parent function. Nothing's transformed. So everything we say, we don't have to count things. That's why I can write it first. So we are going to translate. Now, you don't say where the vertex is. We are describing the transformation. When I graph it, I'll happily just say that vertex is here. But from the vertex at the origin, where is this new vertex in comparison? And we say we translate 2 units left and 6 units down. And that seems to be the only actual change on that particular one. So with that in mind, let's do it. The vertex is at -2, -6. And this has that up 1/1 nature to the graph. So let's just get that one taken care of. Like that. That might be faster than what I was doing before. As long as I don't mess up. Okay. So there's 33. Number 34. C of x equals absolute value of x plus 4. Plus 4. We are going to translate 4 units left and 4 units up. No change in A on this one. And by the way, I'm not graphing, it says graph the given function. I'm not graphing the absolute value of x portion. I hope that's okay. 4 units left, 4 units up. Then up 1/1. Okay, that's number 34. Number 35. Logistically, this is hard to maneuver. Okay, I'll describe it first. So number 35. Let's start with A. I would just go in order, not just left to right order, but also alphabetical order. A, H, K. H-I-J-K. So just start with A. I think they say reflect in the x-axis. I'm going to say reflect over x-axis. Notice that there's no number in front. That means that it's a -1. That means there's no change in the stretch or compression. So I don't have to mention anything there. So reflect over x-axis, that's the A portion. H is translate 3 units right. K is translate 5 units up. And that is very proper description. Mind you, I'm not looking at the answer key from Big Ideas Math, so they are going to probably say reflect in the x-axis and different things like that. But you should say that first. And I might restate why you should state the reflection before the translation on this problem. So I wrote that, which is fantastic. I don't really look at this. I go back to the equation and say, okay, what do I have? And I have a vertex of 3, 5, 3, 5, and then I flip this thing over. Now, it's funny that when I'm, and hopefully it's making sense, my graphing order is different from my describing order. And what I mean by that is, I'm well aware this graph is going to be a flipped over version before I graph it. Like, I'm in the know on that. And furthermore, I'm in the know that that reflection happens regardless of how that vertex goes. But if you told somebody, because when I say flip it over, I'm flipping it over at that vertex. I'm not flipping it over the x-axis. If you told somebody, just to humor you, I'm going to go 3 left and 5 up. If they said, go 3 left and 5 up, and then they said, because here's the thing, we're taking the original graph, right? Let's do this. We're taking this graph here. I say go 3 left and 5 up, and then reflect over the x-axis. Well, you know what you do is reflect over the x-axis. It goes down here, right? I wanted to go 5 up, though. So that's why you have to say the reflection first. Flip it over, here, boom, and then go there. And that's the reason. Okay. I don't think I have time to explain that. Number 36. Reflect over the x-axis. Now, it doesn't matter which way you state those different parts of A, because A has 2 portions. There's reflect over the x-axis. You can say that first, because the negative's there, you might want to. And then vertically stretch by a factor of 3. And then translate 1 unit left and 4 units up. Yeah, I'm not writing all that, so I get to type it. Great. We hit everything. Not only is it A, H, and K, but also A is negative. So we get to do every portion of this. Okay, so I'm just going to look back at the equation. I did the description. That's fantastic. But because I don't have the other graph with me, it's probably not in my best interest to actually go by that description. So -1, 4 is my vertex. And then I'm flipping this thing over. I'm going down 3 over 1. Right? You can see that difference in like how I'm stating one versus the other. You know, I have this formal description, which is important. Understanding and describing transformations. Transformations are a part of math, and they are what you do, and it applies to all these graphs. That's the big thing. This function may be V-shaped, but quadratics aren't. By the way, I have arrows on this. Quadratics aren't V-shaped, right? Log functions aren't V-shaped. So it's important that you know what those behaviors mean, because how the function changes based on A, H, and K is a massive portion of everything we do with graphing, as long as you're in that form. Okay, number 37. Vertically compress or shrink by a factor of 1/2, and then translate 4 units left and 1 unit down. Okay. The vertex is at -4, -1. It goes upward, but it goes up 1 over 2. So I'm going to try and hit that. Up 1 over 2, up 1 over 2. By the way, I just lost count. I think that's right. By the way, I will try and attach graph paper. This same scale, I'll try and attach that down below. Remind me if I don't ever do that, by the way. That's something where I'm time struck, or when I uploaded it, I didn't do the description stuff, whatever. All right, number 38 is one of those instances, all the rest, 38, 39, and 40, are where you really want to get into its proper vertex form, right? So before I describe it, let's get it rewritten better. Factor the 2 out of the inside. Like that. Now I can better describe what this actually has, right? So vertically stretch by a factor of 2. And then translate 1 unit right and 3 units down. I promise I'm a better typer than this. It's when I'm talking and think. I have to talk and think at the same time. With typing, I have trouble. Plus, I have a speaker in front of me. All right. Ciao. Okay. Vertex is 1, -3. I'm going to go up 2 over 1 both directions. Up 2 over 1. Like that. Number 39. Okay, we're going to factor a -1 out of the inside. And then we take the absolute value of -1, which is 1. That makes the A value 1, which means I don't need to write anything. Inside here, we're going to have x minus 1, because the -1 was factored out. I don't know if that makes sense, but that's what we're doing. All right, 39. No reflections, no stretches. Translate. This is a simple graph. Translate 1 unit right and 5 units down, compared to the f of x, the original f of x thing. So I don't really need the bottom of the graph per se. I just need to make sure I get the 5. I do. All right, let's go 1, -5. Go up 1 over 1 from there. Ooh, my head is bothering me. It's kicking in. Okay. Number 40. An hour mark in the video, basically. Got to rewrite that one. N of x equals absolute value of... Oh, excuse me. We're going to factor the -1/3 out. Take its absolute value, becomes 1/3. You factor the -1/3 out, this becomes x minus 3. If you think about -1/3 times -3 is +1. And what's that? +2? +2. Okay. So number 40, we are vertically compressing by a factor of 1/3. prove my typing by saying this first. Translate 3 units right and 2 units up. I'm better than this. I proved nothing. All right. Here we go. Honestly, I should get a... If you want me to ASMR it, I'll get a different mechanical switch keyboard. All right. 3, 2 is our vertex. We're going to go up 1 over 3. Up 1 over 3. Up 1 over 3 like so. And left. Up 1, left 3. Over 3. Like that. Okay. All right. There are those. Okay, number 41, modeling with mathematics. Oh, and by the way, I want to mention, there are too many problems for me to preview what we're doing forward. I haven't seen these problems, so I have no idea what I'm going to run into. I only hope I can do some of these problems. The number of pairs of shoes sold, S in thousands, increases and then decreases as described by the function S of t equals this, where t is the time in weeks. A, graph the function. B, what is the greatest number of pairs of shoes sold in 1 week? Okay, when it comes to the graph, I'm not going to, that other thing is scaled and such. I'm not going to live by a hard and fast rule of scaling and all that. I hope that's okay. I'm just giving you a very rough sketch version of what's going on. If you understand by the vertex form, I know it says S of t instead of S of x, but x is still t, whatever. The HK is 15, 50. You have a vertex at 15, 50, which means over 15 up 50. It's kind of, it's your vertex. The -2 means down 2 over 1, like that. So the graph goes downward maybe a little more sharply than normal. So that's the look of this graph. Okay, that's me graphing it. I hope that's okay. That's just the idea of it. What is the greatest number of pairs of shoes sold in 1 week? After 1 week or in 1 week? Okay, in 1 week. It's where you maximize it. So they're asking for the vertex value, right? When t is 15 weeks, S of t is 50, or S of 15 is 50. 50 is 50,000. What is the greatest number of pairs of shoes sold in 1 week? 50,000 pairs of shoes. If this said, I thought it said after 1 week, so you would plug in 1 into t, and I don't think we're doing that. But there's my basic look of the problem. All right, number 42. On the pool table shown, you bank the 5 ball off the side represented by the x-axis. The path of the ball, give me 1 second. I need this. All right. The path of the ball is described by the function p of x equals 4/3 times x minus 5/4. Okay. Hopefully I don't have to do too much with that. At what point does the 5 ball bank off the side? Well, it's the... Okay. So I don't know how they want me to say, because I don't know what those are. Are these numbers right here? I don't think those are numbers, right? But at the 4/3. Oh, literally, what point? What ordered pair? Okay, that's fine. All right, part A. It banks off at the vertex. So the actual ordered pair is, if you look at the thing, it's 5/4 comma 0. H is 5/4, K is 0. Okay, that makes sense. You can tell I haven't done it. Do you make the shot? Explain your reasoning. Okay, now... You could do this a couple ways. If you were doing the graph, you could say, hey, let's go up 4 over 3. Up 4 over 3 and things like that. But that's kind of difficult when it comes to this being an integer value of 5, 5, and then that not being... What you'd want to do here instead... I actually don't really need this. What you'd want to do here instead is ask yourself, is 5 for x and 5 for y, a solution to your equation? P, being y, is 5. X is 5. Does the left side equal the right side when I substitute 5 for x and 5 for y into this equation? Does that graph cross through that ordered pair? And it seems like it needs to hit it exactly for it to do so. That's the question being asked. So, that's a question. Is this true? Let's find out. Does 5 equal 4/3 times absolute value of, what's 5 minus 5/4? 5 is 20/4. 20/4 minus 5/4 is 15/4. Absolute value of 15/4 is 15/4. 4 times, or 4 over 4 is 1. 15 over 3 is 5. Yeah, 5 equals 5. That checks out. So you know what? Yes. The question was, do you make the shot? Yeah. Now, my reasoning is because 5, 5 is a point on this line that this graph actually does hit that. And in fact, I'm going to have to pause this in a second because I have to get my graph things back probably when we graph again. We'll see when I need to. But 5, 5 is a solution to the equation. It's a solution to the equation. That's the reason. Okay. Number 43. The points A, B, and C lie on the graph of the absolute value function f. Find the coordinates of the points corresponding to A, B, and C on the graph of each function. Find the coordinates of the points corresponding to A, B, and C. Oh, f. Oh, okay. Got it. So f is the function, and it's used in all these equations. Okay. So we're using. So we are rewriting A, B, and C's new points based on the new equation that we have. So on letter A, g of x is going to have a different A, B, and C than letter B. A, B, C. Okay? These are going to have a different A, B, and C than part B's h of x and things like that. Whatever's happening to f. See, f of x is some function, and I'm not determined in figuring out what the actual function equation is. That doesn't matter. What matters is how you are transforming the function. And it may be an absolute value. It may they say it's an absolute value function f. I don't care what it is, but how the function reacts based on what's a, h, and k can help us determine that. So on A, you see this f of x minus 5. The minus 5 is outside of the function as a addition, subtraction. That represents k. That means that everything's being shifted, translated down 5 units. That means the y values are becoming 5 less than they were. If a was originally negative 1/2 comma 3, now it's negative 1/2 comma negative 2. 3 minus 5. 3 minus 5. All the y values are going to become 5 less than what they were. B was at 1, 0. Now this B is at 1, negative 5. 5 units down. C was at negative 4, negative 2. Now C is at negative 4, negative 7. Hope that makes sense. The tricky part is identifying how it's being applied, and I think it might make less sense in this next one. And let's see if you can understand it. Because you don't see it as an absolute value function, other than they told you that it's an absolute value function. F literally being a function is all that's technically needed to know. This next one, h of x equals f of x minus 3. That is within your function. Remember, as an absolute value function, that means it's inside the absolute value. That means that's h. X minus 3. H is 3. H is 3. That means we translate our values 3 units to the right. That means the x's become 3 larger. 3 larger, not smaller. We're not subtracting the x's by 3. The x's have to be 3 larger so we can subtract 3 to them to be the same as the a's were before. If a, the points before, if a was negative 1/2 comma 3, let's make that 3 larger. 2.5 comma 3, 5 halves. 5 halves comma 3. See, 5 halves minus 3 is negative 1/2. That's what gets us that. B, it was at 1, 0. Let's make it 3 larger. 4, 0. C was at negative 4, negative 2. Now it's at negative 1, negative 2. 3 larger. Negative 1 is 3 larger than negative 4. C, j of x equals negative f of x. So that's as if a was -1. That's reflect over x-axis. That means that the y values that were one sign change their sign. The x's stay the same. The y value changes the sign. So the a is going to go from -1, 3 to -1, -1 half, -3. B is going from 1, 0 to 1, 0. That doesn't change. That might be the vertex then. Does that make sense? I don't know. C goes from, I don't know if that makes sense, -4, -2 to -4, 2. Okay, and the last one, D, vertically stretched by a factor of 4. That's the y values, right? Four times absolute value. So A. So the y values become 4 times larger. Sorry, I had a brain fart or something. I'm processing, determining whether I actually need to know the function before this or not. I'm hoping I shouldn't. So -1 half, 12. If there's an answer key that says something different, this is how I'm going by it. 4 times larger. 1, 0 again. And then C is -4, -8. Times 4. Okay? That's 43. All right. Number 44. Explain how the graph of each function compares to the graph of y equals absolute value of x for positive and negative values of k, h, and a. Okay, hold on. It looks like I'm going to type. So, A. All right, what do they want? Explain how the graph of each function compares to the graph for positive and negative values. Okay, so the first one says absolute value of x plus k. So, if k... I think they're saying if k is positive, then blah, blah, blah. If k is negative, blah, blah. If k is greater than 0, positive, vertical translation upward. If k is negative, vertical translation downward. Make sense? All right, B, x minus h. If h is positive, horizontal translation to the right. Now, this is almost one of those things, like, like when I said, like, I'm saying compression is a courtesy. If I use a fraction, like 2/3, and that means that it was a compression anyway. If I say translate to the right, you know that's horizontal, right? But it's a courtesy to say horizontal because that's what h is all about, horizontal translation. So I am going to say that. So if h is less than 0, horizontal translation to the left. I hope that this is what they want us to answer here, how this is working. Yeah, you see the difference between C and D? This is going to be interesting. So this is, yeah. If A is greater than 0. Okay, what do they want? How the graph of each function compares to the graph for positive and negative values. I don't think we have to say if A is greater than or less than 1 or anything like that. I'm not going to talk about the stretches and compressions. No reflection. If A is less than 0, reflect over x-axis. Now look at D. We've talked about D before. Let's say A was positive. You factor it out, you give it its own absolute value, take its absolute value. It stays positive. No change. If A is negative, you factor it out, you take its absolute value, and it turns positive. No change compared to... Oh, hold on. Let's go back to C. A was not part of the parent function. It wasn't part of it. So I do need to mention that part. If absolute value of A, this is going to apply for D as well. If absolute value of A is greater than 1, vertically stretch. If absolute value of A is less than, is between 0 and 1. I already said this for you before. Vertically compress. Okay, That's also going to apply to part D, so I'm going to copy that and make sure that I paste that over, because you know what? That's all I'm going to put for D. There is no change in the, let's see, nope, no reflections. If A is negative, I'm still not going to reflect over anything, and because there's no H, it doesn't change the sign. So that works for me and what I'm doing for the problem. All right, number 45. Whoops. Error analysis. In exercises 45 and 46, describe and correct the error in graphing the function. All right, I'm going to... why didn't that work? I'm going to copy and paste that picture. All right, the error. The error is that they translated 1 unit to the left instead of 1 unit to the right. They translated 1 unit left instead of 1 unit right. Everything else looks fine. So in terms of fixing that, I'm going to graph this over here. And that would be the corrected version. That's number 45. Number 46. Can you see the error in their ways? On number 46. They did not reflect over the x-axis. This graph is right side up. It should be upside down. They never reflected over the x-axis. Their stretch was correct. They went, they went up, but they went, up 3 over 1. They should go down 3 over 1. That's correct. It just, they didn't go down. So it should look like that instead. Okay, mathematical connections. In exercises 47 and 48, write an absolute value function whose graph forms a square with the given graph. Okay, a square. This is just this is geometric talk just for a moment. A square has a couple of properties to them, right? All sides equal, congruent, you would say, and all right angles 90-degree angles. So there are a couple things we're going to have to make sure that we do with this. Let's talk about the right angles first. Because this graph is diagonal, right? It's slanted like that. Then when we go ahead and make a square out of this, then we have to make sure that we, make right angles, over here like that, right? We also have to make sure that everything's the same distance away from 0. Now, as far as right angles go, all we need are opposite reciprocal slopes. If your slope was 2/3, the opposite reciprocal slope is -3/2. You flip the fraction and change the sign is what we're going to be doing with those. So, what I need to do for that problem in particular is, what do they want? Write an equation, write a function. Let's take that graph and bring it over here. Shrink it down in size a little bit. This is basically the graph that I want to make. I want to make this thing, I'm going to give away what it is. I want to make the square basically look like this. This graph has an up 1 over 1 slope, so its opposite reciprocal has to go up 1, left 1. And this is up 1, left 1. We need to make this go up 1, right 1. So there's the first part. The next part is we need to make sure that, by the way, this isn't the only answer. This is open-ended. This is one version of what we could do. I think. The other thing is we need to make sure that it's equal lengths, that this length is the same as this. It's 2 up 1 over 1s like that. Another version of this, we could have done something like this right here. Right? This would have been fine. So there are different versions of this, but the bottom line is we need a function to have a vertex on the y-axis. Yeah, we need to have a vertex on the y-axis. We need to flip it over. A needs to be -1. So what are the things we need? We need A to be -1. We need H to be 0. we need k to be greater than this -2. Those are your only three needs. So this is an open-ended answer for here. Notice it says write an absolute value equation, not the absolute value equation. So, okay, y equals -1 times the absolute value of x plus 3. That works. Or plus 100. Or plus 0, so nothing. Or plus 2, like I first kind of showed. Or -1, or -1.5. But it needs to stay within those parameters. All right, same thing with number 48. Let's just apply the principle and see if we can work it out with the same idea. We need to make sure that the graph kind of is above it. The opposite reciprocal would still be a -1 stretch factor. That doesn't change. But the h now looks like we have to translate it to 3. H has to be 3 this time. And the k has to be greater than, it looks like, 1. It needs to be above that. So these are the only parameters. So, for example, I can do y equals -1 times the absolute value of x minus 3 plus 20. And that should be able to make a square when that happens. Okay. Number 49. Compare the graphs of these two. Okay, well, I'm not going to graph them because they didn't ask me to, but the first one is translated 6 units to the right from the origin. The other one is translated 6 units down from the origin. So Q, the graph of Q, is translated from P, right? P is 6 units right, so I have to go 6 left and then 6 down. Q is translated 6 units left and 6 units down from P. It's kind of all I need to put for that, so that's comparing them, I guess. Okay, number 50. Oh, the object of a computer game is to break bricks by deflecting a ball toward them using a paddle. The graph shows the current path of the ball and the location of the last brick. All right, so it's one of those, and we got to move. We just move it left. Oh, we can move it any direction, up, down, left, or right. You can move the paddle up, down, left, and right. At what coordinates should you place the paddle to break the last brick? Assume the ball deflects at a right angle. And you know what? That's I was going to say that should be left, that's better left unsaid, but not necessarily, because they never mentioned this is absolute values, right? But I want to mention that absolute values are always symmetric. It's tall together, it's compressed together, it never tilts like this, right? It doesn't do that. So whatever's the slope, up 1 over 1 this way is up 1 over 1 that way as well. So this has that kind of slope. If I were to just play with the concept of what's on this side of the screen, you can notice it's going that way. And somewhere we need to go up 1 over 1 this way and hit that brick, right? So somewhere, if I were to cheat a little, right, I need to hit the brick like that. So I can kind of see that answer. Now, is that how you play this thing? Kind of. Actually, you know what? No, I'm not really cheating. That's kind of what you do. You understand that this needs to do right angle, which is not really the way that we talk about absolute values. It needs a slope of 1 and -1, kind of both directions. Where do those slopes meet? I guess that's the best way to talk about this problem, though there are probably other ways to do it. That's the way I want to talk about the problem. So what's the question? At what coordinates should you place that thing? So part A at 7, 1. That's your vertex, right? That's what's going to make that happen. So what did I do there? This is going up 1, left 1. I went the down 1, left 1, because that's the same as up and right, until it intersected with this thing here, and then it hit. You move the paddle to the coordinates of part A, the ball is deflected. How can you write an absolute value equation? Okay, so there's where they mention absolute value, and I like this problem. So your H is 7, your K is 1, and your A is 1. Those are up 1 over 1. So it's going to be y equals absolute value of x minus 7 plus 1, like so. Okay. We have 13 more problems to go. Number 51. Don't ask me to graph. Oh, graph the function. All right, number 51, graph the function. Oh, let me pause this so I can get the other graph axes. Okay, and we are back. Okay, so I have this. All right, graph the function, then rewrite the absolute value function as two linear functions, one that has a domain x is less than 0 and one is a domain x is greater than or equal to 0. Give me a sec, something's making a noise. Okay, 51 is the basic parent function absolute value of x. So just looks like that. Now, what they're asking you to do, and I'm assuming none of the h's change. Yeah, none of the h's change. They're just asking that on these parts here, write the two separate. This is what we would now call a piecewise function. We're breaking the function apart into two separate functions, if you will. One part on the left side and one part on the right side. On the left side of this, if this graph went forever like that, right? Just ignore what's over there. If this graph went like this, what's the equation of that? And in y equals mx plus b form, linear equation, that would be y equals negative x. Slope is -1 and there. This one would be y equals positive x on this side. And that's what those two equations are. Now, their domain mention is that x is less than 0, that's to the left of the y-axis, and x is greater than or equal to 0 from the y-axis onward. That's all they're saying there. Okay, next one. 52, absolute value of x minus 3. Let me just take this, copy and paste it, and translate it 3 units downward. Like that. And turn the color. All right, this is going to be on the left side in slope-intercept form. Slope is still -1, negative x, and then minus 3 y-intercept. And this is positive 1 slope and minus 3 y-intercept. The next one, absolute value of negative x plus 9. If I paste, oh, I probably shouldn't have done the copy-paste thing. Now I can't graph again with these. Can I flip these over together? Yes. Okay. Plus 9 is up here. Okay. Now this now has a positive slope going this way with that, right? So that's y equals x plus 9, positive x plus 9, and this is y equals negative x. Whoops. Y equals negative x plus 9. The last one, I'm sorry, I haven't changed the things. 51, 52, 50. I thought this was part A, B, C, D in my head. Number 54, purple. Let's just graph this one. -4 times absolute value of x. Looks like that. Okay. On this side, it's y equals negative slope, so -4x, and this is y equals positive 4x. Okay. Almost done. Last frame of problems. 55. Graph and compare the two functions. You know, I don't have to pause again. It's just right here. So let me take that, copy, and paste. Okay. Graph and compare the two functions. So, ooh, they get complex. Some do. All right. F of x, g of x. All right. You can see their colors. X minus 1 plus 2, absolute value of x minus 1 plus 2. So 1, 2 is the vertex, and we will go up 1 over 1 like so. Okay. G of x, 1 comma 8. 1 comma 8. And the vertex, we go up 4 over 1. Now that doesn't really fit. I mean, you know, I'll pretend like it does. But, you know, it does that, right? So up 4 over 1 there. All right, compare the two. All right, from F to G, I'm saying this out loud, okay? From F to G, from blue to green. Vertically stretch by a factor of 4. Then translate 6 units upward. Okay. All right. number 56. All right, we got to do some factoring here. This time, actually, I have to write them out. All right, S of x equals, so I'm factoring the 2 out. 2 times the absolute value of x minus 5 halves minus 6. This one, you factor the 2 out, so t of x equals, you factor a 2 out, and then multiply by the 1/2. That's how they interact. 2 times 1/2 is 1, so the a is 1. I don't need to write anything. Factor the 2 out of there, that's x minus 5 halves, kind of like the other one, minus 3. So that's what happens with that factorization. All right, let's graph those two. Minus 5 halves is 2.5, and then minus 6. 1, 2, 3, 4, 5, 6. This is the blue one. Vertical stretch of 2. If I went here, then I'd go 2 over 1 like that. Is that right? Yeah. All right, the green one, 5 halves, and then minus 3. 1, 2, 3, like so. But this has a stretch of 1. So I'm trying to get my color. This is gonna be weird for me to hit. I gotta imagine what I'm gonna do here. Up 1 over 1. Up 1. Is that right? Is that close? You know what? I'm going to pretend like it is. It's kind of weird without the fraction. I'm trying to picture it being above. Okay, what if it was to the left? Okay, let's do that. If it was just to the left, I'd be just above that. I think it'd be like that-ish. Close enough, right? Okay, compare the two graphs. Now we go from blue to green. So although this has a 2, we don't say vertical stretch. We're going from blue to green. We're going from 2 to 1. So we vertically compress by a factor of 1/2. From 2 to 1, it's twice as small. Vertically compress by a factor of 1/2, and then translate 3 units upward. No horizontal translation on that one. Okay, number 57. Oh. All right, number 57. We factor out, they're challenging me, the 3, multiply by negative 2, and we get negative 6. And we're going to get x plus 1/3 inside, plus 4. W of x, y and z. W of x, factor the 3 out, multiplies by the 3, we get 9. Inside we get x plus 1/3 like the other one, and then minus 6. Okay, the blue, 1/3 to the left, 4 up, and negative 6. So 1, 2, 3, 4, 5, 6 over 1. Like that. Normally I talk during this downtime, but this I have to be very particular when I'm working with fractions. Sorry if I have the stern face going. I'm like, ugh, I haven't done this for a long time. So the 1/3 and minus 6 for green, minus 6 right here. Up 9, I could probably only fit one of these sets of points, so I think that's over here. And then over 1 and over 1 like that. So I think that's all I'm really going to be able to fit. Okay, we're going from blue to green. So let's mention A first, going from blue to green. And you can kind of look at the equations and, oh, this is going to be a little trickier. All right, from blue to green, we have to go from negative, okay, we have to multiply negative 6 by something. So take a look. Negative 6 times what gives you 9, right? Divide by negative 6, and we get negative 3 halves. Okay, so what does that mean? Because remember, this original graph wasn't, we're not going to say vertex stretch by a factor of 9 or by a factor of 6 or anything like that. We're going from blue to green. So, first of all, the negative of this means we have to reflect over x-axis. That's the first thing. Reflect over x-axis. Next thing, It's a fraction, but it's a fraction more than 1. So we are going to vertically stretch by a factor of 3 halves, or 1.5. 50% more if you really wanted to. So that's what we're going to say. Reflect over the x-axis. That's the negative part. Vertically stretch by a factor of 3 halves. No horizontal translation. And then we will translate from blue to green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 units down. Yeah. The only thing that I'm stuck on when I say that is, does that take care of translations now? This is where I get a little bit stuck with that. Hopefully I'm saying those right when it comes to translations after the stretch or whatever. Maybe, maybe not. Because if we do that translation part, then we aligned the vertex in the right spot, maybe? I don't know. And that's bad that I don't know. I'm actually trying to think about that now, if that would actually work. I'm going to go with it. It seems appropriate. If it was a parent function, just absolute value of x, then that would apply. So I'm going to stick with it and pretend like I know what I'm doing. All right. Give me one sec. Okay, number 58. All right, c of x. It's standard as far as, probably don't need to write it. Left 3, down 1, or -3, -1 is the vertex, and then up 4 over 1 for the graph. Kind of like that. Okay, and then the other one, oh, I don't have to factor anything out. Cool. Oh, but that, okay. But the y value. All right, -3, comma 1/3 for that guy. And then this is -4/3. So we have to go down 4 over 3. I'm sure I could work that out to find an integer within. I'm not going to bother. Down 4 over 3. I only have to do this a couple times. Over 3 and over 3. Okay. Yeah, now that I think about it, I don't know if I have to describe the translation after. I think once I apply that whole vertical stretch comparison, that might align the vertexes properly. No, it might not. I can't tell. I'm not sure, but I'll try and describe the best that I can from here. Okay, we're going from 4 to -4/3. That one's a lot easier to say out loud. From 4 to -4 would be reflect over x-axis. From 4 to -4/3 is you divide everything by 3. Vertically compressed by a factor of 1/3. And the reason why I bring up why that actually might work is because -1 turns into that 1/3 that way. You reflect it over the axis from blue to green. Reflect it over the axis, it becomes 1. Then you divide it becomes 3 times smaller when you compress by a factor of 1/3. So it might do it on its own. I might not need to do the translation on those ones. You would from a parent function because the origin, the vertex is at the origin, 0, 0. For these ones, maybe not as much. All right, number 59. Describe the transformations from the graph of here to the graph of there. Explain your reasoning. Now, this one is a little interesting because it's backwards from what you would normally do. Normally, we say go from the absolute value of x to -2 times all that stuff. So we would say reflect over x-axis, vertically stretch by a factor of 2, translate 1 left and 4 up. This is opposite. This is opposite. So we got to get to the origin. Right? So we're going to reflect over the x-axis still though, right? We're going to take the negative and turn it positive. We're going to reflect over the x-axis. We're going to take the 2 and turn it to a 1, vertically compressed by a factor of 2. We got to turn to the 1 into a 0. Instead of going 1 left, we got to go 1 to the right. And instead of going 4 up, translate 4 up, we will translate 4 down. So reflect over x-axis, vertically compress by a factor of 1/2, translate 1 unit right and 4 units down. That should get you there. Or do, or do you do the translations first? You might... You might have to do the translations first this time. Translate 1 unit right, 4 units down, then reflect over x-axis, then vertically compress. Because we're going backwards to it. So that makes a little more sense. Okay. Okay. All right, I'm done with that. Number 60. You know what? I'm sorry, I have to type it. All right, 59. Translate 1 unit right and 4 units down. Then reflect over x-axis, vertically compress by factor 1/2. Okay, here we go. All right, number 60. Graph an absolute value function f that represents, oh my goodness, the route a wide receiver runs in a football game. Let the x-axis represent distance in yards across the field horizontally. Let the y-axis represent distance in yards down the field. Be sure to limit the domain so the route is realistic. All right, let me use a graph. Okay, so you're a football player. Let the x-axis represent distance across the field horizontally, y down the field. So if I'm a football player, I could go hike, oh, corner out, boom, go, and touchdown, like that, right? But we want to do an absolute value function. So if I'm a football player, I want to go out from here somehow, somewhere. It doesn't. You can do from the origin, or it doesn't matter where. But I'm gonna go out somewhere, and then I want to do like a corner route and like come back and like here, I want the ball. I think they want something like that, and I can, yeah, I'll totally apply that. So let's do this. Let's hit the corner right there. Let's come back here, which means this is my vertex. So I'm going to go down 2/1 from there, like that. This is totally open-ended, guys. And that's going to be the route. No arrows. This is going to limit the domain. Hike, out here, boom, hit it, come back, boom, I want my ball. And then take it and go later, I suppose. That's going to be my equation. So f. This will be f of x equals, what's my vertex? -4, 6. So x plus 4 and plus 6, and then I said -2 is that guy, right? So that's the equation. That's the function. Limit the domain so the route is realistic. So the farthest left we go on x is -7. The farthest right we go on x is -3. So domain looks like that. So this function with this domain, and you could do whatever you want. This function with this domain provides that graph, and I guess that's a football route that we can use for that. Okay. All right, number 61. 3 more. Excuse me. All right, graph. Number 61, graph. Graph y equals 2 times the absolute value of x plus 2 minus 6 and y equals -2 in the same coordinate plane. Use the graph to solve the equation to check your solutions. Okay, so I'm not going to speak a lot on solving absolute value equations because it's not a part of this thing. It's more about functions. But let's graph those. The first graph has -2, -6 as your vertex, with a slope of 2, if you will. So we'll go, I need arrows again though, in green. All right, up 2/1. Now I don't know if I graphed this right, but the cool thing is we get to solve this algebraically and see if I actually did it properly. I'm not saying I don't know if I graphed it right. I'm saying I don't know if I'm going down this line correctly. I know how to graph them. Okay, yeah, hopefully. The other one is y equals -2. Now I need two arrow. I need a double arrow thing here, and I'm just going to draw it like here. Y equals -2. If you think y equals mx plus b form, the y-intercept is -2. The slope is 0. So it's a horizontal line that goes across like that. Okay. Now, they ask you to solve this. Notice with this equation, 2x, 2 times the absolute value of x plus 2, minus 6 equals -2. They're asking you to solve for... Did they say solve the system? No, they say solve the equation. So we need to solve for x. They're asking what value of x gives you the same y for these graphs. Where do these graphs intersect for x? Now, when I look at my graph by drawing, it appears, let me kind of get that right, it appears that the x values that this thing hits are -4 and 0. Graphically. Algebraically, is that true? That's what they're asking. So we got to solve this. So the way you solve these algebraically is you get the absolute value equation by itself. I'm going to add both sides. I have 6 to both sides. Divide both sides by this 2, and I get that part by itself. Now, because this can be a positive or -2, I'm going to create 2 different equations that say that. X plus 2 can be +2, or x plus 2, can be -2. One or the other. Subtract 2 from both sides here, you get x equals 0. Subtract 2 here from both sides, you get x equals -4. So yes, those are confirmed. Like I said, I wasn't going to spend a long time doing the solving the equations part. That's just the idea of it. Okay, 2 more. Let p be a positive constant. Your friend says that because the graph of y equals absolute value of x plus p is a positive vertical translation of the graph of y equals absolute value of x, the graph of y equals absolute value of x plus p is a positive horizontal oh, this friend, Is your friend correct? No. No, it's not. No, explain. No. As you know, if p is positive inside there, then that'll say x plus inside there. And when it says plus inside the function, doesn't have to be absolute value, just a function. When it says plus inside the function, then we go left. It's a leftward translation. No, the friend is not correct. The friend is not correct. If p is positive, then I don't know. I mean, okay. I'll just say it to you out loud. No, the friend is not correct. Okay, because you're not going to handwrite the rest of it, right? Okay, if p is positive, then that means you have to plug in negative values for x to counter it to make the function 0. Negative values means go left. We want to go right, which means we need to make it say minus p. To be minus p, p would have to be negative, So it's not a positive horizontal translation, it's a negative horizontal translation. There you go. Okay, and last one, number 63, write the vertex of the absolute value function of this in terms of a, h, and k. Why would the vertex... Oh, because you're going to factor it out, I see. All right, so in this last one, this is a lot of what we've done before, but with numbers. They still had fractions, though, so this not really much different. So let's talk about what we've been doing with that. First thing I'm going to do is factor the a out inside of here. Now, when I factor out an a, this becomes a times smaller. H over a is right there. And that kind of already answers the question here. Now we're going to take the absolute value of a and pull it on the outside of here. And this has absolute value of x, or h over a plus k, like that. This is technically your proper form. I don't know if a is positive or negative as a value to begin with, so I have to leave it like that. I can't say the absolute value of a is a, because if a is -2, the absolute value of -2 isn't -2. So I would have to leave it like that. But the vertex form, this x minus h plus k, your vertex is at h. I'm kind of saying h like that because it's not just h. It's h over a, comma, k, like that. You have to get that a times smaller to make it happen. All right, and that is it. That ought to do it for this one. 1 hour and 50 minutes. Thank you so much for watching if you got to the end. And next time you see a video for this stuff, for the Integrated Math 2, it should be on section 1.2. I have no idea what the title is there. All right, take care. I will see you in the next one.